ओके सर, ऑन कर दिया सर। So let's start again. So we were seeing the typical picture of SCM machine. So this is a SCM machine, right? So here you can see electron gun, that is source of electron, and then there is an anode which is kind of collecting electron, and then it is being focused through focusing magnet. And then there is a scanning coil. This scanning coil is there to raster the electron beam over your sample. Finally we get image on the screen. Okay, so why we are opting for scanning electron microscopy? So if you, I request the participants to just take out the disturbance is there. Okay, scanning means here you can see that electron beam is being scanned on the sample. That's why it is scanning. Why electron? Because we are using electron as a probe, and microscopy means a kind of visualizing a small object on higher magnification. So the utility of SCM is microstructure analysis or to surface morphology, and sometimes even we go for 3D investigation and composition analysis. If our system is equipped with the detector, EDEX detector or WDX detector, so we can even kind of analyze the composition of the sample. So earlier optical microscope was used nearly 400 years old back. So okay, what was the problem with the light or optical microscope? It's limited magnification and resolution. Okay, that's why we have shifted to scanning electron microscope. So first we will see the problem with the optical microscope. So if you see, if we define magnification, let's assume this is your picture, this is a squirrel, and if we want to magnify, the same picture is magnified here, and if you measure this distance, okay, assume this distance is small d and this one is capital D. So your magnification is defined as capital D by small d. So this one is capital D and this one is small d. So the magnification is ratio between image size, that is here capital D, to the object size, and it can go up to 1000 kx usually, most of the time, and 40,000 most of the time this 40K is used, and this is kind of 1000 times better than the optical microscope. Now we will see why this is very high magnification with the electron beam. So once we are magnifying the image, suppose if it's not having resolution, so it doesn't make any sense. So magnification, optimum magnification or effective magnification is required. What is effective magnification? Suppose let's consider optical microscope. I am taking example of my optical microscope because most of us are very much familiar with the optical microscope, and we can see object with human eye. Human eye is again you can say an instrument which can see object up to 0.2 mm. Okay, so effective kind of magnification of optical microscopy is again defined by the this your whatever resolution and then divided by your magnification. So effective magnification is defined by this number. Okay, this is why high magnification than the effective magnification only makes the image bigger. So suppose if you are kind of magnifying this image again and again, but the optimum magnification is effective magnification. Even if you magnifying the effective magnification, if it's 10 to the power 3, and if you are magnifying 10 to the power 4 or 6, so you will not see any other detail in the image. So we should always select our effective magnification beforehand performing the SCM images. Then depth of field. Okay, now here you can see two pictures. This is this is focused, but depth of field is no more here. But here you can see the same image is having depth information. This is known as a depth of field or depth of focus. So when you kind of put your object in this range, so your image will be focused, something like this. But if it is out of this, so it will be defocused. So sharpness of object, you can see that it's not here in the second image. However, entire thing is focused in the first image. Why? Because your object is in this range. So depth of field we can define as a range of position for an object in which image sharpness does not change, right? Now what is depth of field? So this is two images of the same object, that is fracture surface of a screw. With optical microscope, you can see lot of reflections. We are not having any kind of useful information from this image. However, if we go for electron microscope, it provides 3D information. You can see something here that some kind of brittle fracture is here. Similarly, there are other information as well. So this is due to the depth of field. In electron microscope, using this kind of setup, we can get good depth of focus or depth of field. Now let's take second example. So this is again IC circuit. This is the optical image, and this is the same image created by the SPM. Here you can see your things are well resolved, and it's having some information about depth as well, right? So this is the definition of depth of field. So SEM machine is having better depth of field than optical microscope. That is why we prefer for the SEM if you are going for the magnification, which is higher than the 1000K. Now the second important point after magnification is resolution. So what is resolution? This is defined as a minimum distance between two objects which can be visually distinguished. Okay, so generally there is limitation for the magnification that is governed by the physics rule, that is diffraction of light. And similarly, resolution is also governed, kind of limited by the diffraction of light. If we go for the formula for the resolution is given by 0.61 lambda. Here lambda is wavelength of your electron beam, mu sin alpha. This entire thing is known as a numerical aperture. So if you see, if we increase this quantity, kind of numerical aperture, we will get better and better resolution, means shorter, small value of R is having better resolution. So somehow we will try to increase this nuclear aperture. And what is the other way to increase the resolution? If we can bring down the lambda value. Okay, the shortest wavelength possible for the optical microscope is 400 nanometer. Beyond this, we can't go. What is the range of the visible light? 400 to 700 nanometer. So shortest one is 400 nanometer. So best resolution with the optical microscope, even taking the maximum value of mu, that is 1. Okay, that is the refractive index of the medium between the imaging plane and objective lens and your object. Okay, so maximum possible resolution with your optical microscope is 0.2 micron, even with using the shortest wavelength. Now let's come to the SEM. So you all must be aware of the de Broglie wavelength or dual nature of the particle and radiation. So as we know that particle is having dual radiation nature. So electron is a particle, it will have dual nature. So what does mean by the dual nature? It will wavelength will be associated by the associated with the particle, that is electron in our case in the electron microscope. Okay, so that is a de Broglie wavelength. If you see, so lambda is equal to h by mv. If we increase the voltage, that is voltage across the column, so we will get shorter and shorter wavelength. Here for 80 kV, you can see that is 0.004 nanometer. If we increase the accelerating voltage, it will go down to the 0.003 nanometer. Generally, typical accelerating voltage in SEM machine is 60 to 100 kV. So you should know what is the role of accelerating voltage in your machine whenever you are acquiring your images. Generally, they keep 80 kV, typical value in any machine. Okay, so the wavelength of electron, if you see earlier wavelength of visible light, it was 400 nanometer. Okay, the probe which we are using in the optical microscope, it is visible light. Okay, what is its wavelength? 400 nanometer. That's why if probe itself is 400 nanometer, we can't see object which is having features shorter than this. That's why we are improving our probe here. So now the probe is some nanometer, kind of 0.003 nanometer. That's why we get better resolution with the SCM machine. So now we are having different probe. Again, resolution I have explained. So here you can see two objects are not well resolved. But if it is resolved, so we can see these two objects very differently, separated, distinguishable. So resolution is defined as a distance at which two or more objects can be distinguished as a separate individual object. Okay, and a resolution for electron microscope is zero point 0.5 nanometer, and for the optical we have seen just now, that is 0.2 micron. Okay, so in the case of electron microscope, it is 1,000 times better than the optical microscope. Okay, so now let's again come to the SCM machine. So it's having electron source, as you can see here. So optical system and then objective lens, which generally produce an electron. Suppose electrons are being ejected from here, and then it comes to the objective and produce electron probe, and that scan the sample. So important component of SCM machine is your electron source, then condenser lens, then scanning coil and objective lens. And then the scanning coil, which will scan our electron beam over the sample, and image will be generated. We will see in a while that how the images are generated in the SCM and TM machine. So again, same thing. So we need sample stage and the detectors. If we want to perform composition analysis, so our system should have detector which are sensitive to X-ray and which can detect X-rays. Okay. So now let's come to the probe size and current. This is very important. Suppose if your beam is started, and what is the probe dia over the sample, that is important. So probe size is very important, and that depend upon various features. That's like this. Let's define probe size by probe diameter. So this is the probe diameter over your specimen. So this will depend upon the probe current, means number of electron, then beam brightness, and the convergence is also very important. So convergence is defined like this, and this is a working distance. So suppose your final aperture is here. So distance between final aperture and specimen is working distance. So all these parameters are very important to define the probe size. Let's come to the now. This is here you have seen beam brightness. Beam brightness directly depends upon the acceleration voltage. That's why when we go for higher accelerating voltage, we get better images. Why better images? As we are increasing beta, so this beam probe size is going down. If we are having probe size is smaller, so we will get better resolution. Now, second thing is convergence angle. Here you can see the convergence angle. Okay, that again depends upon the final aperture. See, I'm sorry. If this aperture is, let's say, this much or this much, so this will change your alpha value. Alpha is convergence angle of the probe. If alpha is smaller, means we will get shorter and shorter probe. If we have short probe size, so we will have better resolution. So that's why alpha depends upon the final aperture diameter. Just now I explained. So this is the diameter of the final aperture. If it will go shorter and shorter, we will get better smaller convergence angle of the probe, and hence better resolution. Now, these are the parameters. Main two parameters are there which decide the probe size, that is the acceleration voltage, and second, the diameter of the final aperture. Okay, so if we try to obtain minimal probe size, we should increase brightness. How we can increase brightness? Just by increasing the acceleration voltage as well as its convergence angle. Okay, so these are two strategies to get minimum probe size for better resolution. Now again the same thing, probably I have explained this, effective magnification in electron microscope. So the resolution of an SCM is controlled by size of electron probe, this size, okay, this type. So this governs the resolution of your image. So that's why we prefer to take images at high acceleration voltage as well as with shorter aperture. With aperture diameter should be short. So this will improve your resolution of the image. Now suppose you are having some probe which is having 10 nanometer dia or DP. This is the size of the probe over the specimen. So the system can have effective magnification up to 20,000. Okay. If you have further decreased the size, your effective magnification will increase. What does mean by the effective magnification? Means it is having useful information. If you are just increasing the magnification, it is possible the image may not have good information. Instead of increasing your magnification, you should increase your effective magnification. How we can increase our effective magnification? By decreasing the probe size. Means by increasing the exciting voltage, by increasing the voltage as well as by modifying the alpha value. So you should always keep in mind the, what happened. Okay, now let's come to the electron specimen interaction. If you are acquiring images, so you know how to improve your effective magnification. The second point is what are the interactions are going between your electron and specimen. Then only you can have better idea how to acquire a good image. So there are different kind of signal generated when this electron is being incident or a specimen. So different kind of signals are being generated. So the first very important signal is secondary electron, that is inelastically scattered. So electrons are coming, they will scatter from the, suppose your atomic system is there, atom is there, and it's their electronic system. So some electron will reflect back or come out of the specimen, that their energy will be different from the energy of the incident electron. That is why they are called inelastically scattered. So the electron which loses its energy on specimen and electron interaction, they are known as secondary electron. Means there is loss of the energy of the electron. Now there are second kind of electron, that is back scattered electron. Means there is no change in the energy of the scattered electron, and that is known as a backscattered electron. So when you're constructing image, so you generally use secondary electron for constructing the image, and this BSC electrons are used for the compositional contrast, and they are ejection of, so this secondary electron, that is there is inelastically scattered, you know, that is what does mean by scattering. A scattering process in which electron loses its energy, that is known as a inelastic scattering. The scattering process in which electron doesn't lose its energy, that is elastically scattered. So elastically elected, that we call it secondary electron, and then elastically scattered backscattered electron. In addition to this electron, there are some X-rays, even optical photons also. So this X-rays are used for the compositional analysis. This is basically characteristic X-rays. Probably I'll be coming to generation of the characteristic X-rays in the coming slide if I'll have time. So there should be detector to detect this X-ray. Okay, so there are two kind of analysis. First one is energy or wavelength dispersive analysis of X-ray. So we analyze this X-ray with their characteristic of the material which is inside your sample. That's why we get compositional contrast inside your specimen. Okay, so this analysis uses characteristic X-rays, and provided there is a detector. So this is the same thing. So your kind of electrons are coming. So here your this is the incident beam. So electrons are being scattered in different directions. So this is secondary electron, if you can see. So there is a secondary electron detector, and there is one more detector, that is backscattered, that detects backscattered electron. So there are different zones from there where this signals come. So let's assume your probe size is dp. So secondary electron comes from top 50 nanometer. And then your backscattered electrons come from 50 to 300 nanometer. Okay. So now your characteristic X-ray come from
guest
the
lecturer.
volume.
Join.
So its depth is quite longer than the secondary and backscattered electrons. The secondary electrons are just coming from the 5 to 50 nanometer, so they are not having much of the energy and they are losing energy. So secondary electron will also be here, but they are not having sufficient energy to come out of the specimen. That's why just stop whatever electrons are generated in 50 nanometer secondary electron means they are losing their energy. They only are able to come out of the sample. And this is energetic electron. They are not losing their energy. That's why signal we get from up to even up to 300 nanometer. So this is again X-ray, hard X-rays. So they are able to come out of the even from the deep inside the sample. Now this is the most important thing, contrast formation. So suppose your sample is having some topographical features or some variation. So what is how the contrast form? Okay, you can see this slide. How you can see this slide? Because it is in black and white. Suppose if I change the color of this light yellow or something, it will be very hard for you to read it. So that's why I have taken black color because it is making good contrast. Okay, similarly, so what is contrast? If we talk in the electron microscopy or image, so in the SCM machine, contrast means number of electrons. So you have different reason. From one reason, if large number of electrons are coming, and from adjacent reason, let's say a small number of electrons are coming, so they will form good contrast. So this contrast means variation in the signal level that correspond to variation in the geometrical feature. Just from the pictures, it will be very clear. So topographic contrast here in the SCM is the primary source for the contrast formation in SCM image. There are different mechanisms from the contrast formation. First one is trajectory effect and second one is the electron mode. You see. So trajectory effect. So suppose your picture is having sample is having this kind of uh, variation, and let's assume a detector is somewhere here. So this is secondary electrons are being emitted and they are directly going to the detector. So from this feature, you will get lot number of electron. But the topography, which is not facing your detector, from here also secondary electron will be coming out, but they are not reaching the detector. So this area will look bright and this area will look dark. This is how this contrast will be created. So the electron emitted from the specimen surface, which is facing the detector, will be collected in the abundance. That's why this phase will look brighter. However, here collection of electron will be poor. So that's why this side looks dull. Okay, so this side will be bright and this side will be dull. Generally, we take image on the gray scale. So if large number of electrons means it's brighter. If less number of electron, it means it will be kind of towards lighter or gray scale. So the electrons emitted from the surface, that depends upon the topology of the surface. What is the feature inside your sample? So that will decide how many electron will emitted from which surface. Okay, and this will create your contrast. If you will understand with the picture. So that's your sample. This is a kind of features, having some features, and this is and here is your detector, secondary electron detector. So whatever electron will be kind of coming out from this surface, B surface, they will come straight to the detector. However, from the C surface, they will go somewhere else. So if we consider this surface means if you see that all the faces which is looking in the brighter, it means they are facing the detector, and if some features are there, they are looking dark, means they are not facing the detector as such. Okay, so this is known as a trajectory effect. And then Then the electron number effect. Suppose your sample is having some kind of feature, means valley and then some hills are there. Let's consider this one. So from here, if you see the when electron supposing hitting your something that is flat, this is your electron probe and this is flat feature. So fewer number of electron will reach to the detector. Okay, so that's why this area will look dull. But suppose if you are having some curved surface like this or this, so large number of secondary electron will reach the detector. So depending upon the topology or curvature, number of what is going to decide contrast in your SEM image, number of electron reaching the detector. So in the trajectory effect, you have seen the faces, kind of faces in your picture, in your sample, which is facing the detector will look brighter. And similarly, suppose some flat surface is there, so fewer number of electron will escape, and that's why this surface will look dark. So the best example is here. Suppose your sample is having some kind of grain structure or some kind of incorporation. You can see this brighter line. This is because they are having this kind of uh, you can say valley. So number of electron coming out of this, they are larger in the number than this is the flat surface. That's why they are looking dull. Sorry, yes, dull, and these are bright. So these are telling that there can be grain boundary or some kind of inclusion or something. Here also you can see some inclusions, means some kind of there is difference in the number of electron coming out of this surface and this boundaries. So contrast formation in SEM is depending upon the number of electron, from which portion how many electrons are coming. I hope it's making sense. If any question you can post or you can keep it with you, I'll take it on one later on. Now the compositional contrast. In the initial only I mentioned there are two kind of electrons, secondary electron which is inelastically scattered and back scattered electron that is elastically scattered. Suppose you are having some kind of element in your sample, okay, and some electrons are kind of being scattered from this. Let's say suppose you are having carbon, this is carbon atom and this is gold. So this gold will have large number of electron. So number of electron kind of scattered from this gold will be higher than carbon. So the area which will be having gold, they will look bright in the image as compared to a kind of atom which having lower atomic number like this. Okay, from this compositional contrast, you can see that these are the area which is having some element which is having high Z number. This is back scattered electron. This is your secondary electron. From secondary electron, you can provide 3D information, but not on the composition. If you take BSc electron, so you will see that some area, even in this, generally we take SC and BSc images together to have fruitful information. So this is your secondary electron image. This is your back BSc electron. So in this you can say, suppose if you are doping, this is your kind of some element which is having high Z number. So this is how compositional contrast is being generated in the SEM machine. Now specimen preparation, that's not tough, but we should take some care. So the first thing is minimal in SEM, we need very minimal sample preparation. First one is the sizing of the specimen, those so that sample can sit on the stuff in the SEM machine. Second thing, this is very important, it should not have any kind of surface contamination. Hydrocarbon, even if we'll touch our sample by hand, that will also spoil your sample. So once sample is clean, we should avoid touching our sample. And before taking our sample to machine, we should clean it by some organic solvent such as methanol or acetone. So just take your some amount of methanol or acetone, dip your sample and put it in ultrasonic cleaner, let's say for 5-10 minutes, and then take out sample with the help of tweezer, but make sure you are not touching sample after cleaning. Okay, now there are just a minute. This is a suppose you are coating. First, you are selecting a smaller area, and this is very resistive. Means you haven't coated anything. So you will see there is some kind of burnout. And if you increase, even if you are increasing the magnification or kind of yes, this is, let's say this is at 10K and this is 1000K. So initially if we focus at, let's say, 10K, and when we are bringing it to 1000K, so you can see this impression. This is not this is not any feature. This is artifact due to the charging in the sample. So to avoid charging, we should go for the some kind of coating. Okay, so this is due to the accumulation of electron. So we anyhow we have to take out this electron from the system. So how we have to avoid charge building on the surface. How we can do that? Sometimes we coat it with some coating, let's say gold or any conductive coating, and then we provide path. So we provide path so that electron can move out from the your sample. So in avoid this kind of image, we have to coat our sample. Otherwise it will give some artifacts in the same image. So here you can see some artifacts. This is very high charging area. We can't see any information. Can you see any information? I can't see. Similarly, these are the very resistive sample. So for resistive sample, we have to coat our sample with subconductive film. Generally we coat carbon or gold, okay, to avoid this kind of features. And this is again some kind of artifacts. This is again due to the resistive nature of the sample. So if we are going for the analytical analysis, we need to coat our sample with carbon or gold. Any conductive coating should be there.
Hello?
Okay, now let's come to the
Mute है.
transmission electron microscope. So transmission electron microscope is very similar to the optical microscope. Okay, so it's having this is tremendous utility in the high resolution microstructure investigation, means less than 5 nanometer, and it can give images at high magnification. In addition, we can get idea about the microstructure as well as structural, means we can have idea about the positioning of the atom. So again, system is very much similar to the optical microscope. So this TM is very much similar to the optical. So we have electron source here, and then set of lenses with to focus the electron beam, and then there is a kind of projection lens, and this is your imaging plane. Okay, typical TM machine looks like this. So as I mentioned, your TM is very much similar to optical microscope. So as in optical, there is source. Similarly, in the TM, there is a source. And then followed by condenser lens, and then your sample, and then objective lens. And then here we see images by eye. Here for the TM, we need phosphorescent screen over which we can project our image. However, SCM is different from the optical and TM. Its strategy is altogether different. Why? Because we are not examining the transmitted electron beam. So this is the first TM machine, which was commercial TM machine fabricated in 1939 by Knoll and Ruska. Okay, later on they got Nobel Prize in 1986. So this is the first TM machine, picture of the first TM machine. So as you all know that discovery of this is a bit of history. I will skip most of the thing, you know, that electron was discovered by Thomson, and the important thing for the electron microscope is de Broglie wavelength. Means particle and radiation are having dual nature. Radiation is also having particle nature, and particle is having wave nature. That's why we are able to go for this kind of electron microscopy. Okay, So this is some history only. I'm skipping it. Then, as in SCM machine, there is elimination system, and then specimen stage. This is here you keep your specimen, and then again magnification, and here the screen over which we see our image, and the data recording system. So this is electron path in a TM machine. Okay. Yes. Here specimen preparation is big tricky. Why it's tricky? Because this electron being transmitted. So we need sample which are electron transparent. So we have to bring down the thickness that is less than 10 nanometer. Sorry, 100 nanometer. So this is a grid we use in the TM machine. And this is a sample particles of a sample, and generally we keep this grid in this kind of assembly, and it's this entire thing goes inside the TM machine. Okay, so the most difficult part in the TM is making sample electron transparent. So first of all, let's take our sample. So we go for pre-thinning, that is we bring the thickness of the sample nearly zero point 0.1 nano or nano, 0.1 mm. Then we make some central lesion which is transparent to the electron by electrolytic thinning or ion milling. Even focused ion beam can be used for the thinning of the in high kind of, suppose if we are preparing some sample, we are taking out some sample, so we have to take help of the focused ion beam for the sample preparation. So sample preparation is tricky in the TM, in the case of TM. Okay, again we'll come to the contrast formation. Okay, as we have seen in the SCM machine, the contrast formation was due to the trajectory effect and electron number effect. Here also contrast formation, contrast is same, however formation is having altogether different mechanism. So two main mechanism are there, that is mass density contrast and the diffraction contrast. Once we will see mass density, then we will come to the diffraction contrast. So in mass density contrast, we define the product of density and thickness at that point. Let's assume your sample, somewhere your sample is here. Okay. So what is the thickness over here and what is the density of that specimen? Okay, that will decide your mass density. And this kind of contrast formation is generally there for non-crystalline material, because they don't have any kind of plane system or periodic structure. So this is main mechanism for the image formation in the amorphous sample. So how we define? Suppose some electron, these beams are being incident and some beam is being scattered and some is passing through the aperture. Okay, so the beam which is passing through the aperture, that is known as the transmitted beam, and the total number of electron which is being scattered from this sample, that is known as ID. So your machine does some calculation, that is C is equal to I0 minus IT by I0. I0 is number of electron which are being incident on the sample, and ID is number of scattered electron, and then IT is transmitted number of electron. This is how contrast is generated in the amorphous sample. So this is again your primary beam, means incident electron. Here is your sample, and then some electrons are scattered and some are transmitted. Some electron which is scattered, not all the scattered electron pass through the objective aperture. We can change the size of objective aperture. So finally, final image is projected on the fluorescent screen. In between, your image is magnified through the help of lenses. So this is the formula to get the contrast in amorphous solids using mass density. This contrast is known as a mass density. Why? Suppose here is your sample, it is having lower density or here high density. So number of electron which will be transmitted, that will change, and this will create contrast in the image. So entire thing is number of electron in the SCM and TM both. So how many electrons are being analyzed, that decide the contrast. Now let's come to the diffraction contrast. So diffraction, as we know, that is a collected deflection of electron. Okay, and this is a primary mechanism for image formation in the crystalline solids. So suppose here we are having, okay, here we are having number of planes. I'm sorry, different set of planes. So electron will come. So you know Bragg's law. So at some angle, that's a theta, the Bragg equation will be satisfied and they will get diffracted in particular angle. So we will collect this information. If we'll collect this electron, they will have information about the interplanar placing of this region. Similarly, suppose planes are aligned in different direction in another region. So whatever electron is being deflected from this region, they will have information about this region. So what happens here? So electron is scattered collaboratively by parallel crystal planes like here. And the electron will satisfy the Bragg's condition. They will undergo constructive diffraction. So if you have you seen, hopefully you have seen that selected area diffraction pattern. So bright spots are there. That bright spots are basically constructive diffraction of electron from the diffractive planes. So probably you have seen this kind of image. So this is very important electron trajectory. So here is your sample. So this is zoom view of this sample. Here you can see parallelly aligned planes are there. Okay. So once your electron beam is coming, they will get diffracted. Only they will get diffracted, which will satisfy Bragg's law, and they will go under constructive interference. Some part of the beam will pass and some will be scattered, some will be stopped even. Okay, now this part is very important to understand. This is your primary beam, this is your sample. Its sample is having some parallel planes. So the point which will satisfy Bragg's law, they will come to the back focal plane. Mind it, this is back focal plane. Okay, here this scattered rays will be focused and they will form dot like pattern. If we kind of take the same thing image on the image plane, we will get this kind of structure. Okay, so the in the diffraction pattern form, this diffraction pattern is always formed on the back focal plane. What is the back focal plane? Means focusing point of the objective lens. We call it objective aperture. Okay, suppose if we want to analyze this area, so just by changing the dia of aperture, we can even look area by. So very sensitive analysis. So this again, suppose if you want to make image, so we will allow to pass through the ray, means beam of electron. So this is again image plane. Basically there are two plane into your machine. One is image plane and second one is back focal plane. If we focus back focal plane on the screen, so we will get a sad pattern. If we focus the just the image part, so we will get image like here. Suppose you are having some inclusion and this planes as well, so the incident beam will get deflected, as well as there will be mass density contrast also. So if you want to take mass density, so you have to focus your whatever is in the image plane, you have to focus on the fluorescent screen. But if you want to go for so this is how we can select. Suppose some inclusion is there, so we can avoid this area, we can take electron beam from the parallel plane. Okay, so there are different kind of mode of operation. So first one is diffraction mode. This is having information about the structural property of material. So your whatever your diffraction pattern is being formed on the back focal plane, that is projected on the fluorescent screen. In the image mode, the image of the specimen is focused on the fluorescent screen. So you have some image plane like here. If you focus this thing on the fluorescent screen, so you will get image of the object. But if you focus this whatever is there in the back focal plane, you will get sad pattern like this. Okay, So there are different modes of operation in the TM machine. First one is diffraction mode. So here whatever diffraction pattern is there in the back focal plane, if we project on fluorescent stream, we will get sad pattern. But if we focus image of the specimen on the fluorescent screen, we will get image of the object. So just by changing the current in the lenses or selecting the aperture, we can switch between these two modes, diffraction mode and image mode. So just by changing the optical path in the TM machine, we can change its mode of operation. So this is again the same thing. Okay, here your sample. So having some parallel plane and something is there, diffraction pattern is there on the back focal plane. If we somehow focus this back focal plane on the fluorescent screen, so we will get a sad pattern. But if we focus this image of the object and magnify it on the fluorescent screen, so we will get image of the object. So there are two mode of operation in the TM machine. So generally your diffraction pattern looks like this. So this kind of pattern is obtained by diffraction from the selected area in the specimen. Like here we have seen, suppose we have some inclusion, so we avoid. First we take image, then we avoid, and then we select some area to take diffraction pattern. That's why we call it selected area diffraction pattern, because this inclusion is not going to give you any kind of diffraction. Okay, so we need to select area. That's why we call it selected area diffraction pattern. Now the kind of the diffracted beam from different plane can be focused in a single spot in back focal plane, like here. So suppose you are having different planes over here or group of plane. So each point over here, this will correspond to one set of plane. Let's say HKL 100. This can be 011. This can be 111. So each point is corresponding to one set of plane. Here from here also you can see that one point is kind of coming from the one set of the beam. So the diffracted beam from the HKL can be focused on a single plot on back focal plane of the objective lens. This is how we get our set pattern. Now this is again important thing, bright field image and dark field image. Suppose if we allow only the transmitted beam to pass through the objective aperture, that will known as a bright field image. If we suppose somehow stop that diffracted beam or the transmitted, that is known as a dark field image. It's clear from the here. So this is a transmitted beam. Suppose if we stop it, so like this, if we stop it, so we will get dark field image. But if we allow to pass through it, we will get dark field image. So just by stopping and allowing, we get different kind of dark field image or bright field image. So in the bright field image, the point to remember that transmitted beam will pass through the objective. So here you can see the transmitted beam is passing through the aperture. So this will give this kind of pattern. Here you can see that even the transmitted beam can be seen. This is the spot corresponding to the transmitted beam. That's why it's very bright. Suppose somehow if we stop this transmitted just by changing the aperture or position of this opening. So if we stop this transmitted and we just are diffracted, so you can see your transmitted is still there, but it is not focused. So generally we can take images on both the mode, bright field as well as dark field. They render different kind of information that depends upon our requirement. So this is again bright field image of aluminum alloy. So here you can see here what we have, the kind of researchers had done. They have kind of assigned the number to the grain 1, 2, 3, 4. And if we tilt the sample, so what will happen? Number of electron reaching the your image plane will change. That's why the kind of grain which was dark in the earlier, it is now bright. So just by tilting the specimen, you can get different information from the same sample. So tilting is vary. So here, suppose if you are taking some image and mark the grain, and now you tilt the sample, the same uh, different information can be taken from the same sample. So tilting is having very important role in TM machine. This is again your dark bright field and dark field image. See here, some whatever area is bright and that is dark here. Generally, we acquire both kind of images from the sample. It gives complementary information. So it is advisable to take both kind of images from the sample. Bright field means we are allowing that transmitted or beam also to pass through. Bright field transmitted, that's why this much brightness is there in the sample, you can see. And the dark beam is main transmitted beam is blocked. Now let's come to the phase contrast. So in the TM, we have seen two kind of contrast. First one was mass density and then diffraction contrast. Both depends upon the amplitude of the de Broglie wave associated with the electron beam. The de Broglie wave is also having phase information, so we haven't used this. Suppose if we exploit the phase difference in the electron beam, which is being the transmitted and the diffracted, so we will have more number of information. This is known as a phase contrast. So generally in high resolution TM machines, we take phase contrast. So in phase contrast, we need minimum two electron wave. Electron wave means the de Broglie wavelength associated with the electron that are in different phase. Suppose if you select one transmitted beam and one diffracted beam, so definitely we need two beams which is having different phase. So if we use these two beams, we will get better contrast, that is phase contrast. Okay, so in any crystalline sample, they are having some, let's say, periodic lattice structure, means periodic lattice plane. So the beam diffracted from this will have different kind of phase information. So this is also used for the kind of placement. Suppose if you are allowing something, interplanar displacing is changed, so it will reflect in your HRTM image. So your HRTM image in your conventional TM, it's having diffraction contrast due to the amplitude of the de Broglie wave. In HRTM, this is the difference phase information. Phase change in the phase is generating a contrast. Earlier, your amplitude was generating contrast, but in HRTM, phase difference is generating contrast. That's why it is very sensitive for high resolution investigation. So here you can see HRTM image. So you can sorry. So you can see these planes are there. Okay, this is the kind of jet contrast. One more contrast is jet contrast. As I told in the SEM, suppose this element is having some element which is high jet value, so that's why there is contrast. You can see some gray area and some brighter area. So that is kind of telling us there are uniform distribution of the germanium. Similarly, the plane separation can also be seen and it can be calculated. And from the this thing, your SAT pattern, you can calculate different thing. I will let you know. So this is again kind of SAT pattern from single crystal. Okay, and now this is SAT pattern from polycrystalline material. Even at looking at the SAT pattern, you can tell what is the nature of your sample. So single crystal is having very well defined spots. However, in the polycrystalline, you can see diffuse rings. Similarly, uh, in the amorphous ring, entirely diffuse ring. Here you can see some dots. So just by changing nature of this single crystal, polycrystal, amorphous material, your SAT pattern will change. Now, how to calculate, how to analyze this kind of, once you're having this kind of pictures with your SAT pattern, now this is very important to know how to analyze. So we have to look for some of the physics. Let's say your sample is something like this, and in different planes are diffracting in different direction. Okay, this is polycrystalline material. So SAT pattern will be something like this. But if your just single crystal is there, if you go analyze the diffraction pattern, so you will get this kind of sad pattern. For polycrystalline material, you will get this kind of diffraction pattern. Okay, and if you kind of do some bit of mathematics, so this is your incident beam and these are your planes. So incident beam is being diffracted on, and this is the camera constant. This is with the TM machine. You can ask for this camera constant. You know the distance. How we can know the distance? Just by measuring the dia of the rings and applying Bragg's law, we get this equation, that is RD is equal to lambda L, means product of R, this distance, and D. That D is interplanar displacing placing. Lambda is wavelength which you are using for the analysis, that depends upon the exciting voltage, and L is the camera constant. This you can ask from the operator. So once you have this information, suppose this is a SAT pattern. So first what you have to do, choose a parallelogram having a smallest R1, R2, R3. The second step should be the measure the distance. This you measure this R1, R2, R3 and then measure the angles phi1 and phi2. Now using the this formula, that is RD is equal to lambda L, you can do small of mathematics from here to get this expression. Theta is very small, that's why we have taken tan 2 theta is equal to 2 sine theta, and then that theorem means sine theta is equal to a bit of mathematics is involved that you can do in any standard book. You can find this. Okay, so first you have to take parallelogram with smallest R1, R2, measure this R1, R2, R3, and then measure angle. Now using the formula, that is RD is equal to N lambda, you can calculate the D value. You have R value. So now this is interplanar spacing. You can compare it with the standard value which is already there, kind of JCPDS files are there. So corresponding, as I mentioned, one spot is representing one plane. Okay, once you know this D1, D2, D3, immediately you can assign some plane. Okay, so this is how this SAT pattern can be analyzed. Finally, you need to check this condition that H1, because this is satisfying parallelogram. Okay, so this condition should be satisfied. Just to cross check whatever information you are taking out from the JCPDS and JCPDS file, that is correct, that is H1 plus H2 is equal to H2 and so on. Okay, so this is the way to get the HKL plane values. These are the sources. So this was all about the electron microscopic characterization of the material. Manoj sir, I am done.
Okay, ma'am. Thank you very much. It's a nice presentation. And now I am asking students and other faculties if they have any question, they can ask. No question? कोई question? Students, any question? Okay, ma'am. I have a question.
Yes, sir.
Can we use this transmission? Ma'am, listening me?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Can we use this transmission electron microscopy to find out stacking fault,
Yes, sir.
line defect?
Yes, sir. I use it for defect analysis. Even line dislocations, point dislocation, stacking fault, tuning of grain boundary, that all can be detected. But sample preparation is a bit tricky here. We can have
Okay,
information
thank
about
you,
the
ma'am.
stacking fault, sir. Yes, sir.
Ma'am, I have a question.
Yes. May I
For
know
time,
to
if
whom
we
I
are
am speaking?
Abhishek got here.
Okay, Abhishek.
Dr.
Yes, please.
Abhishek Gaur.
Yes. Ma'am, for thin films, if material is polycrystalline, how can we prepare a sample for one idea is that we use some sodium chloride crystal and deposit film over that.
Yes, yes.
So what is the preferred way for polycrystalline films?
I'm not getting sample preparation you are asking.
Yes, ma'am. Yes, ma'am. Should we use our standard substrate? There is a preferred growth over some substrate, let's say alumina.
Okay.
Then in that particular case, how do we proceed for TAM?
Okay. For that case, your film will what is the thickness of your film?
In nanometers, around 50 to 100 nanometers.
Okay. For this kind of pictures, generally we take a sample with the help of focused annealing. Okay. So there is first we cut the samples with the focused annealing, then we lift the sample on a TM grade, and then we take this TM grade to the TM machine.
Okay.
Okay. Because your
Ma'am,
sample
he
is
is
less than
saying
100
that
nanometers.
he is making
Sir.
I read one idea that you can like deposit the thin film on a sodium chloride crystal and then we dissolve it. So we have like mesh of the film remaining there and then we take it for the
Okay,
TAM.
but you said your film is having preferred direction.
Yes, ma'am.
So if it is having preferred direction, it will change with the substrate also. Are you studying the substrate effect?
Yes, that's my concern that will it
Yes.
get affected or
So
not?
if you are interested to study substrate effect, because this preferred direction films are very much sensitive to substrate, so you have to go for the FIB cutting. And you can
Okay,
give the
thank you.
sample on TM machine. However, this facility is very rarely available. In my knowledge, it is there in IGCAR, Kalpakkam, IIC Bangalore. So one sample preparation costs just sample preparation cost 4 to 5,000. Must 4 hours of this FIB machine cost you 4,000. And on top of that,
Okay.
analysis means just one specimen is costing 10,000. Very intricate analysis and very interesting.
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Yes. Anything
Thank you
else?
so much. Thank you so much.
Anyone else?
Students, feel free to ask any question. It is fine.
okay. I'm not seeing any student asking any new question. So just going to finish that lecture. Dr. Charu, thank you
It's my pleasure,
for
sir. Thank
presenting
you.
a very elaborative lecture, you can say. And we have learned a lot, although we taught that subject in our MSc
Yes, sir.
and PhD, but today we learned few more things about this subject. Thank you for this. And with this, I am going to conclude this lecture. Thank you very much, ma'am. And I hope we will ask you again for some more interesting topic. Thank you, ma'am.
Sure, sir. Thank you very much for providing this opportunity. Thank you all.
Thank you, ma'am.
Thank you. Thank you,
Thank you,
British. Thank you,
thank you.
Manoj, sir. Yes.
Okay, thank you, ma'am.
Okay, sir. Thank you. Should I end this meeting now?
Okay, ma'am, leaving meeting.
Okay.
Yes, ma'am, yes. Thank you.
Thank you, sir.